Okay, so hello everyone. Welcome to this launch webinar of Irazu version 6.1, which is the latest release of our advanced geomechanical simulation tool. Before starting, I would like to introduce myself and my colleague who will be joining me today in this webinar. My name is Andrea Lisiak. I'm the numerical modeling lead and a co-founder of Geomechanica. I have a PhD degree in rock mechanics from the University of Toronto. At Geomechanica, most of my work focuses on the development and application of simulation tools to solve rock engineering problems. I've co-authored over 50 articles in journals and conference proceedings. And here with me today I have Mr. Johnson Ha. He's a geomechanics specialist with a master's degree in civil engineering, specialized in rock mechanics, again from the University of Toronto. Geomechanica uses Irazu, the Irazu creator, to provide consulting services for a variety of rock engineering problems. His background is in experimental and numerical rock mechanics. The agenda for today, I'll start with a quick introduction of our company, Geomechanica. Then I'll introduce the software Irazu to give a bit of a working knowledge of the package. And then I will talk about the main features and mostly the ones that are new and are introduced with this latest version. And then Johnson will do a live demo of the software, looking at two problems: a rock slope analysis, stability analysis, and a tunnel excavation. And at the end, we'll leave time for some question and answers. For those of you who don't know Geomechanica, our mission is to show you what happens next with our leading edge rock mechanics simulation technology. At the core of what we do is the Irazu geomechanical simulation software, which aims to solve complex rock mechanics problems through cutting-edge high-performance computer simulations. It's a general purpose modeling package which can be applied to several domains where geomechanics and rock mechanics is relevant, such as civil engineering, mining engineering, petroleum, geothermal, and in general research and development. Besides commercializing Irazu, we also offer computational geomechanical consulting services where we run customized simulation analysis using our software for clients. And we also do custom development and analysis. Again, we do this for a wide variety of geomechanical application in several fields. And third, we also have a rock mechanics laboratory here close to Toronto in Canada, which mostly serve the civil engineering and mining engineering markets. The Irazu a bit. So why were the reason for us to develop such a product? And the reason comes from the limitation, mostly from the limitation of conventional continuum-based rock mechanics simulators. As we know, rock masses are often heterogeneous and discontinuous in nature, and therefore geomechanics problems are often related to structural controls, involve large displacement and deformation, as well as fracturing. And for risk analysis, the consequences of failure and therefore the post-peak behavior of the rock mass should be predicted. And therefore there is a need for a simulator that can capture realistic rock behavior and specifically the transition of the rock mass from a continuum state to discontinuum. So the product that we have been working on for several years now is called Irazu, and is a versatile two-dimensional and three-dimensional software package based on the finite discrete element method, and allows the analysis of large deformations, fracturing, and stability in rock masses. Irazu aims to revolutionize your workflow by enhancing safety and efficiency of operation, and also allows to gain novel and unprecedented geomechanical insights, ultimately allowing to streamline operation, cutting costs, and boost productivity. Irazu integrates several multi-physics solvers and advanced features into a single software package, and therefore it can be used to analyze a wide range of geoengineering applications, including but not limited to underground excavation, slope stability, tunneling, dynamic analysis, mining engineering problems, and reservoir geomechanics, both in the oil and gas field as well as geothermal. A quick overview of the software. As I said, is a single software package for all your geomechanical simulation needs in one tool, essentially, which mixes FEM, so standard finite element capabilities, with DM capabilities. is equipped with multi-physics solvers to simulate couple, mechanical, fracturing, hydraulic, and thermal processes with realistic rock mass representation in terms of explicit inclusion of discontinuity networks such as fault, joints, and bending plane. And third, we use high-performance computing and specifically GPU computing to speed up the computation and therefore substantially decreasing the runtime of these models. The software comes with a graphical user interface where the pre-processing and the post-processing can be done without need to do any scripting or editing any text file. And also software gives you open access to both inputs and outputs. Let's look a bit to the key feature, and some of these I will talk in more detail in a few minutes. In terms of constitutive models, at the finite element level, we have linear elasticity, and more recently we have included elastoplasticity. We can incorporate the isotropic as well as a transverse isotropic linear elastic model to capture, for example, the response of bedded materials. We have recently we have added the ability to mix FEM and FDEM material models in one single simulation run. Material and rock mass heterogeneity can be easily captured. We have the ability to capture anisotropic as well as isotropic strength response at the cohesive element level. There is a discrete fraction network generator in 2 dimensions to easily generate the fraction network to be incorporated and embedded into the model. And there are various contact detection models and cohesive frictional discontinuity that can be added. A slide here trying to summarize a bit how the numerical method works. As I said, is a combined finite and discrete element approach. The DM part, or the discrete element part, allows to capture fraction fragmentation, and more specifically, it does so by using what is called a cohesive element approach, where dedicated crack elements are inserted at the interface between the finite elements, and those are the elements that can yield and then fail, and therefore model crack nucleation and growth, both mode 1, so tensile mode, as well as mode 2 or shearing mode. The DM part also includes the contact interaction algorithms, and these are required because either you have existing discontinuities or you form a discontinuity because of fracturing. Now you need a formulation that allows you to capture the contact between fracture surfaces and also the frictional behavior along the surfaces. The DM, this was the DM part, and then we have the FEM part, which analyzes and captures the deformation response and also the damage response with elastoplastic model of the solid element, so the rock matrix. As I said, is only one software package where you can create a geometry, mesh it, build the model in terms of property assignment, boundary condition assignment, and so on, launch the run it, and then visualize the results and do post-processing, as you can see here in the workflow in this animation on the right side. There's the software comes with what you see here is a graphical interface. It's fairly intuitive and modern. There's different solvers that are coupled together: mechanical, thermal, and hydraulic. And the software comes with extensive documentation of the theory implemented, tutorial to help you learn it, verification problems, as well as help pages that are built into the program. Beside the mechanical solver, which was the first one was originally introduced, over the years we have added other solvers, as I said. The hydraulic solver is a modern logic that was introduced to capture flow of fluid inside the fractures, but can also be adapted to capture, with certain limitation, flow of fluid inside the porous rock matrix. There's different boundary conditions that can be applied and vary over time, such as fluid pressure, flow rate, water table, or pressure field interpolated from a CSV file. And here on the right, you see an example of a slow model with a temporally varying water table, and later on we'll have a demo on this. The third solver, which was added more recently, especially in 3 dimension, is the thermal solver. With the thermal solver, you can simulate temperature variation inside the rock mass due to several phenomena. First one is the conduction through the solid and the fluid. Then we have the thermal advection due to the bulk movement of the fluid inside the fractures. There's the convective thermal transfer, which is a transfer of energy between the two phases, the fluid and the solid rock. This is important, for example, for geothermal application. And a contact transfer model, a thermal transfer model, which captures the thermal transfer across these continuities. The thermal solver is fully coupled with both the mechanical and hydraulic solver. Here on the right, you see an animation of a model where a rock sample was heated in order to induce, to break it, for an example of thermal induced fracturing of rock due to the thermoelastic response, coupled thermoelastic response. As I said, one of the unique features, the ability to incorporate discrete fracture network. We have a built-in 2D DFN generator in our graphical interface. These discontinuities essentially mimic the presence of rock mass discontinuities, which are embedded into an intact rock model. Different joint set types can be defined. As you can see here on the right side, different type of fracture network. And each type will require different parameters and statistical distribution for their generation. Once the DFN and these lines in 2D or surfaces in 3D are generated, then you can assign different mechanical properties as well as hydraulic or thermal property to the DFN. Another important feature, which was where we've done some recent work, is the in-situ stress initialization. This is important because in most application, you work with a medium rock mass, which is pre-stressed because of geostatic loading. So traditionally, and the first option that we had to introduce a geostatic stress were the first two listed here. So the uniform stress field, as well as a linearly varying with depth. However, more recently, we have added other option that can be that they improve the application of in-situ stress. Now it's possible to add a linearly varying in-situ stress, but consider the actual topographic surface which as a traction-free surface. You have an example here in this case where there's linear variation with depth of stress, but follows the actual ground surface. You can now import a stress field from a CSV file. So you can define a CSV file where a point cloud, and each point you'll have a stress tensor defined. You can import that, and the software will interpolate the stress value and try to generate an in-situ stress field that honor that distribution. And the fourth one here is the material-based definition. So now you can assign, if this was not possible before, you can assign different in-situ stress tensor or any of this previous option to different materials. Another feature recently added or improved in the latest version concerned the material-based excavation. So if you are to model an excavation, you'll probably be using this feature. So in Irazu, you can excavate a material at any time during your simulation. But what is important, though, in underground excavation, there needs to be a routine to avoid the damage that can be induced by the removal of the material due to inertial effects. Also, when you model at excavation 2D, let's say a tunnel excavation, you need to be able to capture the gradual reduction of radial resistance inside the tunnel due to the 3D phase effects. Okay, so previously, only one method was available to capture this, and it was the so-called core replacement technique. Is the first one here on the top on the right, where essentially the core material will be replaced by a fictitious material, and you will decrease the Young's modulus of that material, and that will simulate progressive excavation, and eventually will be removed. Now we have another main option, which is in line with other geomechanical modeling package, which is called the force relaxation approach. So instead of replacing the material gets removed, but we replace that material with the equivalent forces. So those forces mimic the effect of the support provided at the core material, and then those forces can be gradually reduced over time to model progressive deconfinement. And this is for a lot of applications, this is better because you have better control on the reduction of stress that you want to apply inside the tunnel. And this can also be coupled with a routine that allows to install a liner, install and activate and reactivate a liner inside the tunnel. Another important feature that was recently added is the ability to mix FEM and FDEM material model. Before, your whole model would be an FDM model where you would have cohesive crack element interspersed everywhere in the model. And these elements are important to model fracturing, but often cases, there's area where fracturing does not occur. So now you can assign a FEM, so a continuum model, to those areas. And the main advantage of this is a drastic decrease of computing time. We run some benchmarks, and you can be a model, same model of an excavation. If you assign a FEM material model to the area where fracturing is not going to occur, you can see speed up to 5 times of your runtime. And this is because FEM material model has less degrees of freedom. There's no contact, there's no cohesive element, there's less nodes, and therefore it runs much faster. And also there's a secondary advantage, which is that a pure FEM model allows a more accurate representation of the stiffness inside the material, because the cohesive element introduces a certain degree of artificial compliance in the model. And this development of the FEM part has also paved the way for further development of the FEM formulation. And this is a feature that is not in the version 6.1, but will be released in the next one, and is the ability to capture damage and plastic behavior at the finite element level, same way that you have in a more standard finite element package. Essentially, we can now capture irreversible deformation and damage using continuum-based plasticity theory. And by doing so, we extend effectively the applicability of Irazu beyond quasi-brittle materials. So now you can have a model where you might have your brittle rock, but you can also have other materials within the same model, for example, that are more less brittle and more ductile, such as you can have soils, you can have concrete, or softer rocks, or even metals. And as I said, it can be used also together with the fracturing modeling capability to improve the fracturing simulation by allowing intra-element damage via elastoplasticity at the finite element level. So far, we have added 2 main models, the Drucker-Prager and the Moore-Coulomb, which is widely used in rock mechanics, and more will probably be added in the future. And we'll have this feature in both 2D and 3D. And here on the right, I'm showing some of the verification model that we've been running. This is a tunnel excavating a Moore-Coulomb material. For this problem, there is an analytical solution, and we're making sure that our model can capture the stress distribution in the elastic zone, the yielded zone, with the correct capture of the plastic radius. And one last feature that I want to touch on here is the ability to model rock support, and specifically rock bolts. Rock bolts can be modeled using dedicated 1D bolt elements that are essentially truss elements. These are 1D elements that offer negligible resistance to shearing, bending, and torsion, so they work essentially in tension and compression. Their actual behavior is defined by a 1D elastoplastic constitutive model, but also they are coupled to the rock mass, so to the solid element, by dedicated elastoplastic spring sliders. And this coupling model the effect of, let's say, your grout around the rock bolts and the shearing behavior of that grout. And on the right here, I'm showing an example of application of this modeling capability to an underground excavation. There's 3 cases here of a tunnel where a rock bolt pattern is installed, and there's a decreasing spacing of rock bolts as you move from the left to the right. And the contour here is of displacement and fracturing. The fracture in black, and the color are the displacement around the tunnel. As you can see, as you add more and more support, you can limit the displacement and effectively stabilize your excavation. So just one last slide to conclude here this part. As I said, Irazu is an all-in-one general purpose simulation tool, which can be applied to design and analysis of a wide range of geoengineering application versus having multiple tools for specific application. We are sort of a new generation of expert that is trying to actively push the boundaries of commercial geomechanics simulation tools. And we do so by having a software that is based on cutting-edge research and development, both in terms of computational geomechanics as well as high-performance computing. So with this, I conclude the initial part of this webinar, the presentation, and now we're going to have my colleague Johnson doing a live demo of the software. So Johnson, please go ahead when you're ready.
Thank you, Andrea. Thank you for that great introduction into the Irazu software. So we'll dive now into the live demo. So the first demonstration will be for a slope model. So we actually simulate the stability of a rock slope as it is being excavated, and also simulate the potential destabilizing effect seasonal changes in the water table may have on the rock slope. So here's the start page of the Irazu software. So we can start by going to create a new project, and then we will actually import a CAD file. So ahead of time, I've created the slope geometry in AutoCAD and saved it as a DXF file, so I can easily import it into Irazu. And then once we do that, we just have several import options. So we actually need to enable auto-identify and create surface, and then we can click OK to import. And here you can see I have a rock slope that is 140 meters high, has an overall slope angle of about 52 degrees. Each bench is 20 meters high and 10 meters wide. And at mid height of our rock slope here, we have a 25 meter wide ramp. So here you can see that all the surfaces associated with the problem are shown. So we have 4 surfaces here that will be sequentially excavated during the simulation and the geometry of our rock slope. So with this, we can go ahead and start defining physical names and also the element sizes for each of these surfaces. So we can easily do that by double clicking on each of these surfaces. So here we can call this the rock slope, and it'll have an element size of 1 meter. So it's more of a quality of life feature to name all of your surfaces. You can easily select them when building the model and assign them material properties. Then here we'll have our gradation zone. So call it gradation. I have a coarser element size of 3 meters. And here, about 5 benches deep is our first excavation, and I'll call this a FEM excavation. And I'll go more into detail about why I'm calling that when we build a model. And then I'll subsequently name our remaining 4 excavations here, which I'll call the FDEM excavation. And they'll have the same element size as our rock slope. So again, as we get further away from the rock slope, typically you want to grade our elements. So to do that, we can grade these excavation surfaces to the right here. I can just drag and highlight these about 6 lines here, right click, modify, and I'll grade the element size from 1 meter to 3 meters to this boundary. Now with all of our surfaces defined and element sizes defined, we can actually go to the layer sidebar here. And we can see that if we click on any of these named surfaces, they'll highlight in the visualizer to indicate that we appropriately named our surfaces. The next thing we need to do is to define our boundary conditions. So these are the nodes that we'll be assigning boundary conditions to. So since this is a near surface model, this top surface is actually a free surface, so there is no boundary condition on the top. The left and right edges of the model will be assigned a vertical roller boundary condition. So while holding Shift, again, I can drag and let go to highlight both edges of my model here. Right click, modify, and give it a name. So we'll call it rollers here. And then lastly, the bottom line here will be a pin boundary condition. So I can double click the bottom line and call it pin. And again, on the layer sidebar, you can easily see that the lines were properly assigned just by clicking them. Okay, so I actually include a discrete fraction network in this pink surface here, or a rock slope. So we can easily do that by going to mesh at the top, DFN generator. And here I'll quickly go over some of the features in our DFN generator. So first we need to define our mesh constraints. So I'll actually match the minimum element size to the element size of this rock slope here. So I have 1 meter. And for DFN sets, as Andrea described earlier, there are 4 different types: DFN, persistent joints, non-persistent joints, cross joints, and an imported DFN. So you can actually import your own defined DFN, which you may have from field data or other file formats from other software. So actually stick with DFN here. And then for this discrete fraction network, we can define the dip, distribution model, the length distribution model, and the fracture density. So I'll be adjusting the dip to 30-degree mean with a standard deviation of 5 degrees. But just to show you, there's also a few other distribution models you can use, which are constant, normal, uniform, and homogeneous. And then for the length of fracture density, I'll be sticking with the default parameters. Next, we need to assign this DFN set to the surface, so we can just click rock slope. And I'll add a second DFN set, which will have a mean dip angle of -60 degrees. And again, I'll assign it to the rock slope. So now once I click generate, we'll obtain a stochastic realization of the DFN according to the parameters that were defined. And if you click generate again, you get a different realization of the discrete fracture network. So we can go ahead and close. Now we can see we have our discrete fracture network here. And we're actually now ready to mesh. So we can click mesh at the top. And we'll just give it about 10 seconds here for it to mesh the geometry. And then once it's finished meshing, it's always a good idea to check your mesh quality. So you do that by going to mesh at the top, mesh quality. And you can see for this model, typically if there will be warnings shown if you have poorly shaped elements. So what I mean by poorly shaped elements is generally for triangles, we want to have a minimum angle of at least 20 degrees. And also we want to have an aspect ratio less than 3. So since there are no warnings that are popping up here, I think we're good to go with this mesh. So now we can go into the project building portion of the this model. So we can go to project options at the top. And then here we can give our project a name. Define the project units for our simulation here. So it'll be meters here. And we want to enable mechanical and hydraulic modules because we're assembling the water table. And we want to enable in-situ stresses. And we do have a discrete fracture network in our model. So we can click OK. So I'll quickly walk through the entire modeling process here. So the model will initialize the pre-modeling in-situ stress field using the finite element method. And this is done strictly for computational speed up and efficiency reasons. And then following initialization, the first 5 benches, so this material here, will be excavated also in FEM, and the stresses will redistribute according to the rock slope geometry and boundary conditions until the model reaches equilibrium. And then following that, that will be the starting point for our FDEM simulation, which is where we'll insert crack elements between all the finite elements to allow fracturing to occur. So in our run options here, we'll first, enable FEM run, FEM output files, and it will enable gravity in the Y direction. And then in our time sequencing here on the right, we actually have 3 different time sequences that we will be using. So add 2 here. And then first we'll have 700,000 mechanical time steps for the FDEM excavations. And that would be followed by 4 by 100,000 hydromechanical coupling steps. So this is the stage in the model where we introduce the water table and temporarily vary with time. And then finally, we'll have 3.9 million mechanical time steps to simulate run out of the rock slope. And then next we can define our material properties. So for this model, we have 6 materials. So we can quickly generate 6 materials here. And we can name them, call them rock, FEM excavation, and the 4 FDEM excavations. And then once we have created materials, we can easily assign them to the mesh. So at the top here, there's a tool called assign based on lookup table. So here I can cross-reference the element sets that I defined during mesh generation with the material sets that I just created. Okay. So once successfully assigned, you can see that the color of the elements adopt the material property. And again, in the layer sidebar, we can see that that we have 6 sets that were assigned, and we can easily show and hide each material property. So let's edit the elastic properties of our rock. So we can go to edit, and we'll change the density of the rock to 2,700 kilograms per meters cubed. We'll have a Young's modulus of 50 GPa and a Poisson's ratio of 0.25. We'll adjust the strength properties here. So the cohesion will be 5 MPa, our tensile strength will be 2 MPa, and our mode 1 and mode 2 fracture energies would be 5 and 50. And click OK. And then we can easily propagate these properties into the remaining sets here, or material sets here. So we can right-click on rock, click copy into, and we can select all of our other materials here, click OK and yes. And then now you can see that they have adopted the density and strength properties that I changed earlier. Okay, so with our materials defined and assigned, now we can define our excavation sequence. So by going to edit under advanced properties, and then going to the excavations tab, we'll enable FEM excavation for our FEM excavation model, followed by enable for the remaining materials, which would be excavated away in FDEM, and they'll all use the core modulus reduction method. So here I'll define the time step at which the material will be removed from the simulation. So starting at 250,000 time steps, I'll remove each layer every 100,000 time steps. Then we can click OK. And then here you'll be prompted on whether you want to use the default core modulus reduction method. So as Andreas briefly described earlier, this is to reduce the Young's modulus of the material over time in order to ensure that we don't get potential unwanted dynamic effects related to sudden removal of the material in the model. So we'll use this option for this simulation. So we can click yes and view, and we can see that the Young's modulus of the material will be reduced from 50 GPa to 0.5 GPa, and I'll adjust it so that we do this process over 100,000 time steps. So here I'll modify the remaining layers or the remaining property or material properties here. And then we can click OK to accept all our changes. So now we have all our materials defined and our excavation sequencing defined. Next, we will assign our boundary conditions in the boundary conditions tab. So for this model, again, we have 2 mechanical boundary conditions, which are the rollers, the vertical rollers on the side, and the pins along the bottom. So we can quickly change these in the tab in the window below. And then to assign them to the mesh, we can right-click and then click our rollers nodes that we previously defined, and then assign them rollers Y. And I'll just change a display option here so we can see that the nodes are properly assigned. So then we can see the nodes are properly assigned here. And then next, here we'll create our hydraulic boundary condition. So we can add the hydraulic boundary condition, and here's where we use one of the new features in Irazu 6.1. So we'll go to hydraulic, custom hydrostatic pressure, and here we'll add CSV files. And these CSV files contain the coordinates of all of the 4 water tables that we will be importing. So I'll quickly import them by selecting all my CSV files, and then I'll click apply, and then OK. And then you can see here that I have 4 water tables that were imported. And the layers tab, we can see the time at which each water table is activated. But the first hydraulic step, this will be the first water table. And then the last hydraulic step, this will be the last water table. So over time, our water table is increasing, kind of mimicking the effect of a seasonal increase in the water table in the rock. So next, we'll define our discrete fracture network. So as we had shown before, we have two sets of discrete fractures that were generated. So we can add two discrete fracture properties here, and they'll be both broken type. And I'll just adjust the strength properties to a 0.3 friction coefficient for both of them, which is approximately 17 degrees friction angle. And then lastly, we can go to in-situ stresses. And here we'll define our in-situ stress. So we'll use a linearly varying along Y in-situ stress type. So that means as we increase with depth, we'll increase our in-situ stress as defined by our delta sigma Y and delta sigma X parameters in this window. Here we'll actually use the use actual ground surface function as well. So we actually want to use or assign a 0 in-situ stress to the top line here, and as we increase with depth, we'll increase our stress. This is a very simple application of this feature, since this is a straight horizontal line along the top. However, if you have topography in your model, it'll actually use the actual topography to as your datum and increase the in-situ stress from there. So the vertical in-situ stress that will increase per meter will be 26.5 MPa, which is approximately equal to the density of the rock, 2,700 kilograms per meter cubed, multiplied by acceleration of gravity, so 9.81. And the horizontal in-situ stress will be roughly double the vertical in-situ stress. So with this, all these parameters defined for a model, we're actually ready to run. So we can click run at the top here. But I've actually run this model ahead of time. So I'll quickly just jump over and show the results of the model. So here you can see our starting point in the model, all of our fractures, discrete fractures in the rock slope are already broken. So you can see them in the visualization here. And you'll also notice that 5 benches have already been excavated away. So this is the excavation process that took place using the finite element method. And then the stresses were recalculated based on the rock slope geometry. So I can quickly show the principal stresses here. So you can see this is our starting point from our final FEM step. Then I'll just change this to displacement, and I'll play through this animation. So you can see as these benches were excavated away, there's some fracturing that developed in the rock slope as a result of the removal of material. And as we continue, eventually you'll get some failure along the slope. So I'll just back up a bit in this simulation result, and I'll change it to the fluid pressure to be plotted. So you can see at this frame that the first water table is introduced. And then the next frame, the water table is increasing and further increasing. Eventually, it reaches near the rock face, and you eventually get catastrophic failure originating from the ram. And that's sliding along a pre-existing fracture. So let's fully animate this, and then we can see the run out of the material into the bottom base of the slope. Okay, so this concludes the first demonstration. So now I'll go through our second demonstration. So we'll be simulating the progressive deconfinement and excavation damage zone of a tunnel. We'll use 2 new features that are the latest release of Irazu. So we're going to be mixing FEM and FDEM material models, as well as using the force relaxation excavation method. So we'll start by creating a new project, and we'll create a mesh in geometry. So we'll draw our geometry this time in Irazu. So first, I'll use the draw rectangle tool to draw my exterior domain, which is a 100 meter by 100 meter square. So snapping to the grid here and looking at the coordinates at the center bottom of the screen, I'll pick the first point of my square, and then the second point of my square at 50, -50. And this will have an element size of 1 meter, so I can set element size here. And then next, I'll draw my refinement zone, which will be a 24 meter by 24 meter square in the center of this domain. So I can change my grid sizing here, so I can easily snap to the grid to draw this. And then I'll pick my first point on my square and the second point. And I want to embed this surface within the larger one. And then lastly, we draw the tunnel here. So I'll draw a circle, arbitrary circle to start, and then go over to the selection tool, highlight the circle I just drew, and at the bottom here, I'll just change the radius to 1.5 meters. And then I'll drag this to the center and snap to the grid. So now let's, again, similar to our rock slope, we'll name our surfaces and define all our element sizes. So here, since this is my exterior domain, I'll call this the FEM zone. This will be the zone where I do not expect fracturing to occur as a result of the material excavation. So this area will actually be assigned the FEM material model. Then my refinement zone, I'll call it the FDEM zone. So this is where the region where I expect fracturing to happen. And I'll change the element size to 0.1 meters. And then my tunnel here will have the same element size as my FDEM zone. And if I open my layers, you can see I have 3 surfaces defined. So now let's go ahead and mesh. And then as always, we want to check the mesh quality. So you go to mesh quality. And then you can see that there are no warnings generated with any poorly shaped elements for this particular mesh. So we're good to proceed and start building out our model. So we'll give our project a name again. And our project units will be in meters. We'll only be using the mechanical calculations for our model. And we want to enable in-situ stresses. So here we'll run our model for 300,000 time steps. And we'll output model results every 10,000 time steps. And FEM run and gravity will be disabled for this run. Then we go over to the materials tab. And here we have 3 materials. Again, our tunnel, our FDEM zone or a refinement zone, and our FEM zone. And then again, we can assign them to the mesh using the assign based on lookup table. And then we go cross-reference them with the material sets that were defined during mesh creation. And again, they'll adopt the color of the material property. And here we'll adjust the material properties. So we can go to edit under tunnel. And the Young's modulus will be 10 GPa of this rock. And the strength will be adjusted as well. So we'll use a cohesion of 10 MPa, a tensile strength of 2 MPa, and a mode 1 and mode 2 fracturing of 5 and 50. And we can propagate these properties into the other material sets using the copy into function. And then lastly, we need to change our FEM zone material model. So since we don't expect much fracturing to happen, we can actually not insert cohesive crack elements into this green area here. And that will significantly speed up computation time without sacrificing accuracy in our modeling results. So to do that, we can, under FEM zone, go to edit. And it's as simple as changing material model to elastic FEM, no fracturing. And you can see when I did that, a few tabs here disappeared. So the strength properties and the penalties tab disappeared. And that's because those are no longer needed, as those are properties associated with the crack elements. And then next, we'll assign our boundary conditions. So since this is an underground excavation, we'll pin the exterior boundary of this model. So we'll add 1 boundary condition, change it to pin. And to quickly select the boundary nodes here, we can use a keyboard shortcut Control A, and then assign them the mechanical pin boundary condition. And then lastly, we'll define our in-situ stresses. So we'll use a uniform in-situ stress field. And in the horizontal in-situ stress, we'll assign 15 MPa. And then in our vertical, we'll assign it 25 MPa stress. So now with our model complete, we can click run here, and then we can run our model. But I've actually run this ahead of time. So I just bring it over to frame here, and we can visualize the results together. So here you'll notice as soon as we open the results, there's this black box here. So what this black box is the interface between my FDEM zone and my FEM zone, or my fractionable and unfractionable zone. So that's just there to kind of show where that interface is. So here I'm plotting displacement, and as I play through the simulation, you can see at some point my model gets excavated away, and they're actually replaced by relaxation forces. And if I continue and reduce the relaxation forces in my model, at some point we'll get fracturing in the FDEM zone. And then at this point of the simulation, the excavation is completely unsupported. And then we can see that we get fracturing. And then if we continue to play this, we get spalling into the unsupported excavation. So this was using the force relaxation excavation method, where we remove the material and replace it with supporting forces. And then another note is I've actually run this exact model using a full FDEM model and compared it to this model, which has the hybrid FEM and FDEM material models. And for this 2D excavation, we actually get a 20% speed up in our runtime, and we didn't actually sacrifice any accuracy in the final modeling result. So with that concludes the live demonstration of the webinar. I hope that you enjoyed it. And now I think we'd be happy to take any questions you may have. And if you do have any questions, please type them in the Q&A section of Zoom.